Hi, my name is Savanna. Today I'm presenting my master's project from the capstone for the GIST at the U of A. And my project was to assess the habitat value in Sonora for the Leopardus pardalis, or more commonly known as the ocelot. So just a little bit of history. The U.S. Fish and Wildlife Service listed the ocelot as endangered in the United States in 1982. There's actually some dispute among researchers about whether or not Arizona was included in the natural range for the ocelot. So I've prepared this map with two different data sources for the ocelot range. The one in hatching is by the USGS. They're really just focusing on the United States, and they have Arizona and Texas listed as the range. I did the hatching because it seems to be based on like limited historical sightings and stuff in Arizona. We don't actually know if there's a breeding population of ocelots in Arizona. It appears that there isn't, because I feel like we would know about it. So currently the most northern breeding population of ocelots is in Sonora, which is where I decided to do my project. But just a little bit more about this map. The dark gray is the ocelot range as reported by the International Union for the Conservation of Nature. They kind of give a more global perspective, and they prepare something called this red list of threatened and endangered species. And the ocelot is on it, so they're tracking all these species for their risk of global extinction. And they categorize the ocelot as least concern, which is good news for us. So I just kind of wanted to highlight that distinction where it's an endangered species in the United States and it's listed as least concern on a more global perspective. So that's kind of nice to know. And I also prepared a web map to kind of highlight that map. So here's a little, hopefully you can see it, video. We're zooming into how the Texas range has a disconnect there. So even though there is such a wide distribution of the ocelot's range, we want to make sure we don't isolate any portions of that range, and we want to preserve the furthest extents of the range, like in Sonora and just barely into Arizona. So why does all of this matter, right? So there's actually been a lot of countries who are meeting up for this big biodiversity conference, and they have pledged their commitment to preserving 30% of the world by 2033. This is known as like the 30-30 initiative. So globally, we're at 16% of land and inland waters and only 8% of marine areas. Sonora is only at 10% conserved area. And on the left, I have some graphs. These are also prepared by the International Union for the Conservation of Nature. Globally, species survival is going down. Mexico isn't as bad, but it's still not great. So we have a lot of room to grow there. And I wanted to focus on Sonora for this project because I found that research was identifying it as an area that needed more exploration, and particularly corridors moving north into Arizona. They need more exploration. And I thought that this whole project would bring more awareness to these issues and whether or not there needs to be more protections for the ocelot in the United States. So to do this project, I did a lot of research on what kind of geographic variables the ocelot prefers, what type of variables they choose in their home ranges. So just like kind of quickly, that's like tropical, subtropical, thorn scrub areas. They technically like the higher elevation. They like dense tree cover, and they like to be close to lakes and far from roads. And they don't care so much about rivers, it turns out. So to kind of translate all that information into something that I could do an analysis on, I compiled all of this data from these different sources. So I got my elevation data from SRTM. I used land cover to extract things like the deciduous forest and subtropical areas, and so on. The global land discovery analysis is where I got my tree canopy cover data. And the North American Commission for Environmental Cooperation is where I got the data for lakes and for roads. And all of these different data sets needed to go through a lot of transformation before they were ready for use in the suitability model that I created. So for example, the lakes and roads, to calculate the distances between them, I had to do this thing called Euclidean distance, which just is like a cell-by-cell distance for, it created this really nice raster. But then I had to classify everything. So you can see my little tables here of how I classified each raster. Then finally, I had to add weights to each raster to kind of emphasize different variables more than the other. I wanted to prepare multiple models so that I can compare them against each other. So the final raster suitability was just a raster plus. It was actually pretty simple. It was all the data transformation and getting it ready for input into this model was the hard part. Running the actual model was basically just adding each raster together. So I had 5 inputs, which meant that the highest score possible was a 5. And the result were, they had some checkerboard being in them where, like, you know, this was bright green and that was bright red, and there were just 2 cells right next to each other. And I felt like that wasn't very accurate in the real world. So to kind of help like generalize that data, I felt like it needed to take an average. So I used the focal statistics tool and I specified a neighborhood of 9 and a radius. So it calculated the average on a cell-by-cell basis using that neighborhood, which helped to kind of blend edges and reduce some of those checkerboards. And I think it really created a better effect. So just kind of going over the model a little bit. My first model, M1, that one was really focusing on like the water sources. M2 was a closer look at elevation. M3 I used as kind of like a comparison, so it just had equal values for each parameter. And then M4 I weighed really heavily on the road presence. Overall, the best performing model was M1. I think the high score in that one was like a 2.6. So it's actually important to note that none of the models returned a perfect score. So this wasn't like a Boolean suitability where it's like, is suitable, isn't suitable. It was really more meant to be interpreted on like a fluid scale. So these areas are like performing better, they have higher value, and these places are performing less well, so they have lower value. So that's really the way I wanted these results to be interpreted. So I will give you a look at them right now. So model 1 is the one that focuses on water sources. So you can really see kind of like concentric rings around those water sources. And the area that's most suitable in this model, and actually all of the models, is to the east of Hermosillo. There's another town over there called Savarripa, probably saying both terrible. But that area there east of Hermosillo and kind of north of Savarripa are the areas that performed the best in each of the models, as well as that area far south on the eastern border of Sonora, basically just kind of coming off of the Sierra Madres. So model 1, you can see the water sources pretty clearly. Model 2 follows a little closer along elevation ranges, still scoring high in similar areas. And I also want to draw attention to, you can actually see the differences in suitability going north. There are kind of north-south corridors. There's 2 of them actually, which is great. Let's take a look at the next ones. Model 3 is that one that was just kind of to compare. So it has everything weighted equally. So you can still kind of see those concentric rings from the distance to water sources. And then in model 4, you can see pretty clearly how the roads kind of cut through these areas and shrink them. So if distance from roads is a really important factor, then those areas get smaller and smaller. There's a lot of information that are being presented by these rasters. I mean, this is a huge area that's just being summed up in one map, and I feel like that's not a really great way to present information. So I also created a web app that allows the user to really interact with the data and get a closer look. So you can see there's like a base map toggle, you can zoom right in, you can compare between 2 different models, how the areas performed. And I also included a couple bookmarks, so you can kind of zoom around to different areas of interest. You can switch the bookmarks there too, or the base maps, I mean. And now it's showing one of those corridors going north. So very cool. I think the web map is a great way to engage the audience with your data more than just a static map could. So yeah, that's actually pretty much it. Overall, I think that all of the models performed pretty well. The areas that performed well in every single model are areas where we have known populations of ocelots. So I think that's great. And I was able to identify some of those corridors leading north. I think that there should be some additional research done on how the ocelots disperse through their environment, because just because there is suitable habitat that leads north, we don't know if that's actually how they traverse through their environment. But GIS is a great tool to use for informing conservation research. It provided a really great visualization, and I think that this can help raise awareness about this cause. And I have a link to the web app so you can get to know it a little bit more. But I also wanted to just close on that amazingly an ocelot was just spotted in Arizona very recently. So it was just great timing since I was wrapping up on my project. I had like 5 people send it to me. They were so excited. So yeah, it's a rare visitor in Arizona. It's really cool to see it. And this was a really fun project to work on. So thank you. That's all I have.
Great work, Savanna, on your project.